Okay, this video is, I guess, a somewhat of a public service announcement here. Um, we're certainly talking about functions here in 1151, and there will be all sorts of different kinds of functions here. Exponential functions, trigonometric functions, logarithmic functions, inverse trig functions, polynomials, roots, and so on. And the most famous kind of function, probably number one in the BCS poll of functions, is the linear function here. Y equal to good old mx plus b, where m is the slope or the rate, b is kind of your starting value of y there. At least at x equal to 0, we call the y-intercept. This happens a lot of times. This is a function there that, by its very nature, has the same rate or the same slope. Okay, and as it turns out, and I challenge you to geometrically argue here why the graph of such a function will turn out to be a straight line there. In other words, it won't curve off at any place. And these certainly are useful here in their own right in situations where, say, you're earning the same amount of money on a job. So for every hour that goes by, say you're earning $9 an hour at McDonald's or something, and for every hour that goes by, well, you are going up by $9. Okay, so this would be a $9 difference there going up. Every 2 hours you'd earn $18, and so on and so forth. You also talk about same price of an item. So you have $2 per gallon at the grocery store for milk. And so if you buy 6 gallons, you'd know that your price would go up a total of $6, or six times 2, which is $12, in addition to the rest of your grocery bill. Also, the classic case, of course, is you're driving down the highway on cruise control, always at the same speed, and you are going at 55 miles an hour. And so for every hour that goes by, your position will increase by 55 miles. Every 2 hours, be 110 miles, and so on and so forth. You can learn a lot more about particular equations of lines. Where does slope-intercept come from? Why does point-slope form of the line make sense? In another video here. I believe that video is called Equations of Lines. But what you need to be careful about here is that not every function and not every situation in real life has a constant rate going on. As x changes, y does not always change at a constant rate. If we had only linear functions, there would be no need for this course. There would be no need for calculus, because calculus studies functions that are jealous of lines. They don't go at the same rate all the time. In fact, they have curves for their graphs, and the rate at one value of x is going to be completely different than the rate at another value of x. For example, here, the rate here, we're going to call that kind of, if we put a line with that and going at the same direction that that graph is going in at that same value, we would find that it would have a much, much different rate or different slope than the value, say, here. This would be a negative slope. This would be a positive slope. So here you would be going westward. Here you would be going eastward, say, if we were talking about our driving in our car situation. What happens is calculus, at least the differential part of it here, we'll be studying here is what is the exact rate of change at a particular value when the rate's always changing, when you've turned off the cruise control. And essentially what you're doing here is you're taking a picture of your speedometer, now technically if you had it, the velocinometer, on your car at any particular time. And obviously the picture will be a still picture of, say, 48 miles per hour. And that means your car was definitely moving at that instant of time there. To address these issues, as you might guess, because we only know about rates of change when it is under cruise control in a linear case here, we actually take advantage of those cases there to help us approximate what the rates are on curves. when that rate is always changing. So although not every function in the world is a linear function, be careful. Don't think that everything's a linear function. Don't catch that disease. Um, we will be using our vast knowledge of linear functions in figuring out the tougher problem. So we're going to take what we know and work to what we don't know.